All right, so we did a little bit of a warm-up, and we found inverse operations for this stuff, and we came to the conclusion that this operation should have an answer, but we don't know it. We compared it to something like where we do know the answer. Only limitation right now is that we don't have an inverse operation for this yet. So the whole point of today is to introduce you to this inverse operation, which is called a logarithm. We can look at problems like this that should look familiar. Any recognition to this type of problem? I'll give you a time frame. March 2013 would be the approximate time frame where you would have learned to solve things similar to these. Now, why were these all nice? What did we do in order to solve these things? I'm hearing a couple people say it. Common base, change the bottom. We could get these things, if we get both sides in terms of a common base, we could solve them. The problem we run into is we do not have, for example, in 2 to the x equals 7, 7 is not a power of 2. So we're not going to write 7 as the power of 2 in order to solve in that manner. So there's got to be another way. So here's our objectives for today. We started with the first one already. The first one is to establish a need for logarithms. We need an operation that takes the variable out of the exponent. Number 2, I understand at an exponent. We're just going to, it's a pretty simple pattern development skill here today. If you can learn to write something that looks one way, writing it in another way, following a prescribed pattern, you're going to be all right. And I can evaluate logarithms without a calculator. So we already kind of talked about this, but the point of today is there's a need for another operation. 2 to the x equals 7, 4 to the x equals 9. Now, we could kind of predict what type of number this could be. What type of number for x would solve something like that? Big numbers, small numbers? Is it going to be nice? Rational or irrational? Probably irrational. Do we have a range of values that x could fall into? Okay, I heard somebody say 2 to 3. Jacob, how did you come up with 2 to 3? 2 to 3. Okay, so you're bookending it. You're saying 2 squared is 4, and you're saying 2 cubed is 8. So x in this example has to be somewhere in between 2 and 3. And I also heard somebody, Jake over here, say it's got to be probably closer to 3 than to 2. There's going to be a decimal involved. Okay, so we'll do more stuff with a calculator, and you'll find out what the actual answer is to this tomorrow. But first I want to just establish a need for an inverse operation. Because adding undoes subtracting, multiplication undoes division. All those things that we talked about on the warm-up slide. Okay? All right, here's the definition. And this is in your notes, but I'll add a couple of things here to annotate it as well. But the key here is this phrase in the middle is really important. Is equivalent to, means it's the same as. So we have spent a lot of time over here. This is our comfort zone at this point. We refer to b in an expression like this, refer to b as what? The base. It gets an exponent on it. It is the base. And x is the exponent. Okay, and I don't really, you're not going to provide a name what a is. It's an exponent on a base. Okay? Whole point of today is to be able to take something that looks like 2 to the x equals 7 and write it so that x isn't in the exponent anymore. And the way to do it is with this definition. I'll identify some things over here as well. B, I've color-coded this nicely for you. Do you like that? B is known as the base. How do you remember that? Starts with the same letter, but unfortunately on your worksheets, it's not going to be a form. How do I? There. It's below. It's the low part. It's down below. Any music gurus out there? The bass is the bottom part, right? If these are equivalent, what does x refer to? The exponent. Exponent, yeah, if you want to do that, that's fun. That's a little play on words. I like it. I like it. And I'm gonna on this definition over here, on this side of the definition, I should say, I'm gonna add a qualifier here. This number that goes right here is referred to as the argument. That's the argument of the logarithm, and I don't really know of a fancy way to remember that, but that's the argument. Sure. Okay. So what this is basically saying now, if I take this statement here, 3 squared equals 9, everybody agrees that's true, right? There's another way to say that 3 squared equals 9. Now, Mr. Best, 3 squared equals 9 makes sense. Why would I want to write it another way? Well, in this example, you wouldn't need to write it another way. But the other way to write it, and I'm going to write out my wording of this because I want you to use the appropriate language when you do it. 3 of 9 is 2. I'm taking the logarithm of 9 with base 3. And kind of develop into some more understanding as we go here, but I have to specify the base, because the base could be anything I want. If the base was 2, I'd be dealing with powers of 2. If the base was 3, I'd be dealing with powers of 3. The base can be anything. Okay? So what this is going to allow us to do is it's going to allow us to solve things like 2 to the x equals 7. So on your own, take 20 seconds, use the notes from the previous slide to rewrite 2 to the x equals 7 as a logarithm. Go ahead and take 20 seconds to do it. Right, the x, if you don't, even though you don't know what x is, you can still put it in the logarithm equation as x in the right place. Okay, show your answer to a neighbor. Okay, hopefully you have log base 2 of 7 equals x. The 2 is subscripted, which means it's little, it's smaller than the other numbers, and it's set below. Yeah. The advantage of this now is this. Where is x? It's by itself now. X is by this statement. We didn't have an inverse operation a few moments ago. We said it had to be between 2 and 3, but we didn't have an inverse operation to get the x out of the exponent. Now, I told you a definition. We don't really know exactly where it came from or how these numbers are approximated. Well, some people do, but that's not important to you at this point. But the idea here now is if I know how to do a log base 2 of 7, I can find the value for x. Now, this problem in particular is a calculus problem. And this is something that we'll go further with tomorrow. So today your job is to understand the definition. Tomorrow we will evaluate this and find out exactly what that number is. Well, approximately what that number is, because it's irrational. Okay? Oh, this is it. This is the big understanding for today. If you're given an exponential equation, its exponent result, you need to be able to rewrite it as a log equation and determine which one is useful. Okay? Kind of depends on where the exponent's going to be. But here's 2 examples. Log base 2 of x equals 5 doesn't have a lot of meaning to us, but we could write it in another way that might help. How else could I write log base 2 of x equals 5? 2 to the 5th is x. Could you tell me what that is now? I hear it, 32. X equals 32. Okay? The point of this is as follows. These two equations are equivalent. They mean the same thing. If a log is useful, use a log. If an exponent's more useful, use an exponent. Okay? Here's an exponential form, 4 to the x equals 12. Let's rewrite it as a logarithm. What would I write first? The word log. What goes after the word log? 4. Is it up here? Nope. I need to do what to it? Microsoft Word language. Subscript it, make it small, and put it down below. Of 12 is the argument of the log equals x. Now, if I have a calculator, I can do this. Because we're not going to do the calculator. Okay? All right, here's two ways of looking at these. I'm going to show you how to evaluate some logarithms without a calculator. Here's two ways of looking at these things. We're going to do the more of the verbal learner approach and the visual learner approach. We're going to do both. So we're going to look at log base 3 of 81, and I'm going to write a question. That's what that statement means. What is the exponent on 3? Because 3, right? How do I know the base is 3? It's the one set down below. What is the exponent on 3 to get 81? Do you know the answer to that question? It's 4. Anybody see that that's 4? Now, before 10 minutes ago, 20 minutes ago, you didn't really know what log meant, did you? But could you have answered this question? Probably. Let's do one more. Log base 8 of 1. Write the question and answer the question. What is the exponent on 8 to get 1? What is it? 8 to the 1 is 1? 8 to the 0 is 1. If 0 is the exponent on 8, the result, the argument is 1. Cool? It is 0. Well, I'm going to write it in another way in just a moment. You have a good point. It does say 1. But the point is this. Log form is written as this. The more visual, this is the verbal way of learning these things. The visual way of learning these things would be this. If the base is 8 and the result is 1, what's the exponent? 8 to what power is 1? And it's 8 to the 0 power. Well, 8 to the first power is 8. 8 to the 0 is 1. Anything to the 0 power is 1 from our exponents unit. Okay? So the point is this. I'm going to move on to the visual part in a moment because some of you are more verbal learners, some of you are more visual learners. But the point is this. A logarithm is an exponent. And I can prove it by doing this. The exponent is x. The exponent is x. The exponent is equal to a log expression. So really, to solve a log, to evaluate a log, I'm answering the question, what is the exponent? Okay? Here's the way I like to look at these things. I'm more of a visual learner. I know some of you like to use words, some of you are more verbal approach. But the way I like to look at these is as follows. 5 is the base. How do I know? Because it's set below. I don't know the exponent, because the exponent's always the thing that goes on the other side of the log. But the result is 1 over 25. That's not 25. That's 25. It's like a 25. Okay? Now at this point, we're back to last negative. Okay, but it's not negative x squared. All we want is the exponent, negative 2. So I'm squaring. Negative 2 is the exponent. So it's negative 2 as the exponent in order to solve that, or find the value of that logarithm. We're evaluating. Okay. Next one. The base is 7. The exponent is unknown, but I know the result is the square root of 7. Can I think of an exponent makes this statement down here true? What exponent is the same as a square root? It's a square root. It's a square root, so it's a 1/2 as an exponent. Okay? Enough for example on that? Okay, just a quick summary. If you're asked to evaluate logarithms, it's easiest at this point to rewrite them as an exponent. Rewrite them as an exponent, and then we can go back to last chapter, and we can find the appropriate exponent in order to make that. Okay? When we're given stuff like 2 to the x equals 7, you don't have an answer for that yet. So all of the things on tonight's homework are going to involve no calculator, so they're all going to be stuff like we saw in the exponents unit. The point of this is you need to be able to use the definition to rewrite exponents in log form and logs in exponent form.